Have you ever wondered about this problem? In a multi-core CPU, when core 0 and core 7 access the same variable simultaneously, are their values actually consistent? If core 0 just changed variable x to 2, will core 7 see it immediately? If not, what happens? In reality, the consequences could be disastrous. This can lead to data races, dirty reads, deadlocks, and even bizarre crashes. Yet, modern CPUs manage to maintain logical correctness, relying on an extremely complex but critically important mechanism, the cache coherence protocol. Today, we will dive deep into two mainstream protocols in modern CPUs, MESI and MOESI, and explain how they keep data synchronized and consistent across dozens of cores. Let's start with the fundamental issue. Modern CPUs don't access main memory every time they access cache, because L1, L2 cache is tens to hundreds of times faster than main memory. Suppose a variable x is stored in memory. Core 0 loads x equals 1 into its L1 cache. Core 1 also loads x equals 1 into its L1 cache. That's fine, but if core 0 modifies variable x, core 1's cache still holds the old x. This is the stale data problem. If both cores modify x simultaneously, the later write overwrites the earlier one, causing a write conflict. Worse, if core 1 reads x immediately after core 0 writes it, but doesn't see the new value, that's a read after write inconsistency. This is the cache coherence problem. Without a coherence protocol, multi-threaded programs would exhibit completely unpredictable behavior. Data updates could never synchronize properly. Distributed locks, queues, and concurrency primitives would fail. Data structures could read ghost values. Therefore, the CPU must uphold a basic principle. If any core modifies a cache line, all other cores must be notified immediately. This is the mission of MESI and MOESI. In modern CPUs, each cache line has 4 states. This is the core of the MESI protocol, which solves multi-core data consistency issues through state transitions and a bus snooping mechanism. Modified. The data in the cache line has been modified by the current core and differs from the original data in memory. This cache line is valid only in the current core's cache. Other cores must obtain the latest copy from this core if they need to access the data. Exclusive. The data in the cache line is consistent with memory, and the current core is the only one holding a copy. The core can modify this cache line directly without notifying others, and its state changes to M state after modification. Shared. The data in the cache line is consistent with memory, and multiple cores hold copies. If a core needs to modify this cache line, it must first notify other cores to invalidate their copies, then change its own state to M state. Invalid. The data in the cache line is stale and cannot be used by the current core. When the core needs to access the corresponding data, it must reload it from memory or another core. How is state synchronization achieved? Through 2 actions. First, snooping, where each core monitors the system bus and knows about all read or write requests from others. Second, state transition. For example, if a core sees that another core has modified a cache line it shares, it sets its own state to invalid. Understanding write operations is key to grasping coherence. Let's use the read-write interaction on variable x between core 0 and core 1 as an example. First of all, core 0 reads variable x. Core 0 sends a read memory x request on the bus. Other cores snooping the bus find they have no copy of x in their caches, so they don't respond. Core 0 loads the cache line for x from memory and sets its state to exclusive. Now core 0 is the sole owner of x, and the data matches memory. Next, core 1 reads variable x. Core 1 sends a read memory x request on the bus. Core 0, snooping the bus, detects this request and finds it has an E-state cache line for x. Core 0 sends a copy of this cache line data on the bus and simultaneously changes its own cache line state from E-state to shared. Core 1 receives the data and sets its cache line state to S state. Now both cores hold valid copies of x, consistent with memory. Then, core 0 modifies variable x. Core 0 needs to modify x, but its cache line is in the S state. According to MESI rules, core 0 first sends an invalidate request on the bus, telling all cores holding a copy of this cache line to mark their copies invalid. Core 1, snooping the bus, receives this request, changes its x cache line state to invalid, and sends an acknowledgement response on the bus. After receiving the acknowledgement, core 0 changes its cache line state from S to modified, and then performs the write operation. Now core 0's cache line data differs from memory, and core 1's copy is invalid. Finally, core 1 accesses variable x again. When core 1 tries to read x, it finds its cache line is in the I state. Thus, it sends a read memory x request on the bus. Core 0, snooping the bus, finds it holds the M state cache line for x, and immediately performs 2 operations. First, it writes the latest data from this cache line back to memory or sends it directly to core 1, depending on architectural optimizations. Second, it changes its own cache line state to shared if only core 1 requested it, or keeps it as modified if other cores also request it simultaneously. Core 1 receives the latest data from the bus and sets its cache line state to shared, completing the data load. MESI works well, but has a drawback. Every time shared data is modified, other copies must be invalidated, causing additional latency and memory bandwidth consumption. How is this optimized? AMD and some ARM and IBM power processors use MOESI. The MOESI protocol adds an owned state. Owned means this core holds the most recent data, and other cores can also have copies in the S state. But these copies are borrowed from the O state core. The data in memory is stale. What does this mean? Here's an example. Core 0 modifies X, entering the modified state. Core 1 wants to read X. Core 0 sends the latest X directly to Core 1. Core 0's state becomes owned state, and Core 1's state becomes shared state. This way, memory doesn't need to be updated and data propagates directly from core to core, resulting in higher performance. This is a very clever optimization. MOESI can significantly reduce memory writebacks and bus traffic. Now, let's discuss the pitfall programmers most easily fall into: false sharing, which is almost a nightmare for all multi-threaded programs. The conditions for its occurrence are very simple. Two different variables reside in the same cache line, are frequently written by different threads. For example, in the code snippet shown on screen, if A and B happen to fall within the same 64-byte cache line, thread 1 modifying A causes the entire cache line to be invalidated. Thread 2 must reload the cache line when reading B, and vice versa. Thus, the two threads interfere with each other, causing constant invalidations. The final result might be slower than single-threaded execution. This is false sharing. The simplest solution is padding, adding unused data before and after the variable to ensure each variable occupies its own cache line, avoiding sharing with others. Alternatively, separate frequently modified variables from others physically, for example, by storing state variables for different threads in separate arrays rather than together in a single struct. Although cache coherence protocols are implemented in hardware, the way software engineers write code directly affects the protocol's efficiency. As programmers, we need to remember 4 key points. Avoid false sharing. Use padding or separate variables. Don't let unrelated variables share a bed. Minimize multi-threaded writes to the same object. Think of it as avoiding having multiple people grab one microphone. Try to let them do their own work separately. Use atomic instead of locks. Atomic operations are hardware implemented and much faster than locks, but be careful not to misuse memory ordering. Experiment with lock-free data structures. For example, lock-free queues can reduce thread weighting. Programmers who don't understand CPU coherence won't be able to write high-performance code. If you enjoy more in-depth content on computer science, don't forget to subscribe. See you in the next video.